In the previous video, we have used the rainfall data and fitted two simple exponential smoothing models, one with a value of alpha equals to 0.2 and another with a value of alpha equals to 0.8. We have observed that the model with the value of alpha equals to 0.2 fits the data much better compared to the model with alpha equals to 0.8. If you have not watched the previous video, then give it a look. In this video, we're going to particularly discuss how to choose the optimal value of alpha and how to interpret the value. Let us first create a grid for alpha starting from 0.05 to 1.0 at an interval of 0.05. So we have a total of 20 values in this grid from 0.05 to 1.0. Now we will use a for loop, and using each alpha in this grid, let us first fit a simple exponential smoothing model, get the value of SSC for each model, and finally plot the fitted model in every iterations. Note that inside the for loop, alpha of the HoltWinters function is set to A. This is what changes at every iterations. Inside the plot function, we have used a paste function to write the main. The paste function is used to paste two or more strings together. For example, paste I, love, statistics will paste these three strings into a single string. So if we have a variable, let's say SSE equals to 1020, then paste of SSE equal to SSE will give a string saying SSE equal to 1020. We have used this function here so that with every graph we can print the value of alpha and the corresponding value of the SSE. This code sys.sleep1 function makes the program wait for a second before the next iteration starts. Now let us run this loop to see what we get. This gives us 20 plots, one for every model. So this for loop gives us 20 exponential smoothing models, and we can kind of see that the SSE increases with the increase in the value of alpha. A better way to observe this would be to plot a graph between SSE and alpha. But before we do this, let us do a slight modification to our previous code so that we can store the SSE values in a vector. To do this, we create an empty vector. Let's name it SSE. Now, inside the for loop, let us add a line which will allow us to add the values of SSE to this vector named SSE. To understand this, let's say you have an empty vector x. Now, if you update x such that x equals to cx, 1, then this would add the element 1 to the vector x. In the same way, if you further update x as x equals to cx, 2, then this would add the element 2 in the vector x, and the updated vector x now contains two elements in it. And this is exactly what we are using over here. Before we run the for loop this time, let us put the sys.sleep in the comment line. And now let us run this loop. And now this time, this vector SSE contains the SSE values for all the models. Let us use the names function to add names to the elements of this vector as per the values of alpha. So these are the values of SSE for different values of alpha. And we can kind of see that the SSE increases with the increase in the value of alpha. Let us now plot this relationship graphically using the plot function. Using type equals to b, we specify that we want both line and dot in this plot. From this graph, it is absolutely easy to understand that this exponential smoothing model is suggesting us to choose smaller values of alpha to better fit the data. The optimal value of alpha would be the one for which this SSE would be minimum. This value can be obtained automatically using HoltWinters functions by setting alpha as equal to null, which is in fact the default setting. Using this, we found out that the optimal value of alpha is 0.02. This means for any value of alpha other than this one, the value of SSE would be higher. If you have already watched my previous video on simple exponential smoothing, then you probably understand what choosing a small value of alpha like this one would mean. Such a small value of alpha indicates that forecasting for the next time point will be based on both recent and past values. In fact, with this small value of alpha, the forecasting model will include many observations in the past from the series to forecast the future. Look at this graph. In this graph, we have plotted the values of the weights against different time points. Please refer to my previous video on simple exponential smoothing to understand how the weights are calculated. And we can see with this small value of alpha of 0.024, the forecasting model although gives smaller weights but does not ignore the values which are even very far in the past. This also means that the series is controlled by both recent and past events. Now, let us look at another example, a little different one this time. Let's say this series represents the demand of a certain product starting from 1975 to 2020. In this example, although we have both levels and trends, we will ignore the trends part for a while. This graph clearly shows that the level of the series keeps changing with the change in time. In fact, the level changes abruptly as the time changes. Now, if we read this data in R and do all the things we have done using the previous time series on rainfall, then you will be able to observe that the model keeps fitting the data better and better as the value of alpha increases. If you look at the SSE values, you will find that these values decreases as alpha increases. Now let's find the optimal alpha for this model. Using the HoltWinters function and setting alpha equals to null and keeping the beta and gamma parameters as false, the optimal value of alpha comes out to be 0.99992, which is approximately 1. In the video on simple exponential smoothing model, I left you with a question. What kind of model will you get if alpha is equal to 1? Like in our case. The answer is pretty simple. If you put alpha equals to 1 in the simple exponential smoothing model, then you get ft equals to ft minus 1, which is nothing but a naive forecasting model, a model which you have learned in one of my previous video in this series. So when alpha is equal to 1, this would mean that the forecasted value in the next time point is equal to the value of the series in the immediate previous time point, which means a simple exponential smoothing model reduces to a naive forecasting model when alpha is equal to 1.